Hello, students. We have lists, we have sets. What if we mix them up? What if we try to put sets and lists and sets? I mean, we already know that we can do something like this, where you can have tuples inside sets. What if I tried, say, a set? I change these to sets now. So I want the set 1, 2 and the set 3, 4, 5 inside our set. And some people might worry about things like sets of sets that do not contain themselves from the Cantorian, dilemmas that arise. But we run into an error much quicker here. We are told that this is not hashable. Okay, what does that mean? Well, a hashable object in Python is one where it has a hash value. And there is a function called hash that assigns values to things. So for instance, I could see that the tuple 3, 4, 5 has a value. Okay, we could go all out here, but we're not going to. For our purposes right now, hashable objects are ones that we can stick inside sets. So what's hashable? Well, integers, floats, and some types of tuples. I say some types of tuples because we don't want to stick a tuple like that inside a set, because that's a way of sneaking a set into a set. So that's not going to work as well. So if you want to know if something can be placed into a set, you can always run this function called hash on it and see if you get a value. For instance, if I do this, it's going to tell me no, there's no hash value for that. Okay. What about lists? Can I stick a list inside a set? And once again, lists are not hashable as well. So tuples containing hashable objects are hashable. Sets, lists are not. Okay. What about putting sets, lists, and tuples inside lists? Well, we can have a list of tuples. 1, 2, 3, 4, 5. That works fine. What about a list of sets? 1, 2, 3, 4, 5. That works fine. What about a list of lists? 1, 2, 3, 4, 5. Those all work fine. So lists don't care what you would put in them. So why would sets care what you put in them, right? Why are sets so fussy? Well, just for one example, things that are not hashable like sets and lists, we can change them. There are going to be different things that we can do that change what a set is. And you don't want sets of things that are changing. Let's say you have a set with two things and they're different. So you have two elements in the set and then they become the same. Now you have one element in the set, but then they become different again. But you already have a one element set. So when you only have one thing in the set, it's not going to see you have two things, and it's going to cause all sorts of havoc. You don't want that. So we have a way of seeing what we can put into a set, and we don't want sets of sets. But lists let us put everything inside lists. That sort of problem wouldn't happen, because if you have sets that are changing, well, each one is in a different spot in the list, right? Because lists allow for repetition. They're an ordered collection. Okay. So you know what? I'm looking at this list of lists over here, and I'm thinking to myself, could we do a matrix? Like, what is a matrix? Well, a matrix is basically a box of numbers, right? Where you put something like 1, 2, 3, 4, something like that. And I should put some comments there. So that's an example of a matrix. Basically just a box of numbers, right? Rows and columns. And I could do this with a list. I could do, say, 1, 2, 3, 4 here. And in fact, one thing that I could do is I can access the elements inside my matrix. However, remember that Python starts counting everything at 0. So let's say I want the entry of this matrix, or no, let me make a different one because I don't want to use those numbers. 6, 7, 8, 9. Boom, that's my matrix. Let's say I want the entry in row 0, column 0. Well, what I can do is I can just do a double index. So why is this working? Why am I having a double index? Well, think about what's happening here. If I just call 6, 7, 8, 9, 0, what do I get? Well, I'm going to get the first element of my list, right? Because the subscript 0 is saying, hey, grab this first element. This first element's a list. And then when I grab this, when I see this index, Python's going to give me the 0th element of this list, which is 6, and that's why I get 6. So for instance, if I want the entry here that's in row 1, column 0, I can just enter that, and I'm going to get the element in row 1, column 0. Why is that? Because I'm going to get the first element of this big list, which is going to be 8, 9, and then from that list, I'm going to get the 0th element of that list, which is actually just 8. So I can have lists of lists, and they behave as matrices. As a matter of fact, let's say I want matrices with 0 and 1 as entries. And we'll just do the 2 by 2 case. Okay, so one thing I could do is I could say, okay, I don't want a set of these matrices because we can't put lists and sets, not hashable. But what I can do is I can do something like this. I can put lists of lists inside a list. So we're going to have a list of lists of lists. Okay, a little tricky to say. But one thing I could do is I can just call the elements A, B, and C, and D. And I could say for A in range, I want 2 there, because they could be 0 or 1. For B in range 2. For C in range 2. For D in range 2. Okay, and you'll see I get all of these matrices here. Now, if I just wanted to know how many there were, well, then one thing I could do is I could stick all of this inside an len, right? I could do that, and I get 16. But another thing that I could do that would be a shortcut here is I could say, okay, you see, I don't need the actual matrix itself, and I know that my A, B, and C, and D are going to determine the matrix. So what I could do is I could just stick a 1 there, put a sum here, and add 1 for each of those. And maybe that makes it clear as to why there's 16 matrices, because you have 2 different choices for A, 2 for B, 2 for C, and 2 for D. And 2 times 2 times 2 times 2 gives us a total of 16 possibilities as we branch out. Another thing that we could do is we could play around with determinants a little bit. Now, what's the determinant of a 2 by 2 matrix? Well, if I have a matrix of the form A, B, C, D, I know the determinant is AD minus BC. So suppose I wanted the determinants of those 2 by 2 matrices. Well, one thing I could do is I could take something like this, and I could say, okay, what we have up here, but I don't want the matrices themselves, I want their determinants. So, once again, I don't have to put the matrices in the map part of this comprehension. I just put the determinants inside the this map part of the comprehension, and I see, okay, I've gotten these with repetition, but what if I just want to know what they are, right? Because that's, maybe I don't need to know which determinants go to which. So I will do something like this. And these are all the possible values of determinants that I could get with matrices in 0 and 1 as my entries. So suppose I now let 2 be a possible number. I want to know what determinants can I get if I have a 2 by 2 matrix where the entries are 0, 1, or 2. And now I see I can go all the way up to 4 with 2, or just out of curiosity, how big does this get if I allow 3? And you'll see now it's starting to grow here. You might want to guess a pattern here, because we have 1 when we get to 2, we have 2 squared when we get to 3, we have 3 squared when we get to 4. That's something to experiment with. But what I want to go is, I want to go in a different direction here. I want to talk about invertible matrices. So those of you who know linear algebra know that a matrix is invertible if the determinant is non-zero. So suppose what I want is I want the number of invertible matrices with entries in 0 and 1. So basically, what I want is I want this determinant right here to be non-zero. Well, let's go back, because we'll go back and create, we'll use a sum function. And I want to sum 1. When do I want to sum 1? Well, I want to sum 1 whenever AD minus BC is not 0. So that will give me the number of invertible matrices with entries in 0 and 1. And we could actually see what those matrices are, if I wanted to, by instead saying, okay, instead of a sum, I want a list here. Why don't we list them? So now I can see what those matrices are. And yes, this line is too long, but let's run it anyway. And I can actually see the matrices that are invertible. So nice little exercise. There are other ways of dealing with matrices in Python as well that are very efficient, especially if you grab some libraries like the SIMPy library. But we might talk about that stuff a little later.